Your body is made of stardust from galaxies far beyond our own. This is not just a beautiful idea, it is a scientific fact that connects our deepest origins to the most violent and creative forces in the cosmos. You are about to discover 24 astonishing links between distant galactic events and the very existence of our planet. By the end, you will see Earth not as a solitary world, but as a direct product of the universe's grand history. How did a galactic collision billions of years ago determine the iron in your blood? Why does the invisible pull of dark matter keep our planet's core alive? We are about to trace our lineage back to cosmic cannibalism, stellar explosions in neighboring galaxies, and the ghostly reign of intergalactic particles. This journey will permanently reshape your understanding of home. What does it truly mean to be a citizen of the cosmos? That iron in your blood has a violent and spectacular origin story. It was forged inside a star much larger than our Sun, a star that could only have been born under the most extreme conditions. These conditions are often created by a process known as galactic cannibalism, a cosmic event of unimaginable scale. When a large galaxy gravitationally shreds and consumes a smaller one, it is not merely a destructive act. The immense collision sends powerful shockwaves rippling through clouds of gas and dust, compressing them and triggering a ferocious firestorm of new star birth. Astronomers call these events starbursts, and they are the universe's most productive factories for heavy elements. Inside these stellar nurseries, giant stars are born. They burn through their nuclear fuel in just a few million years, a blink of an eye in cosmic time. Their deaths are even more spectacular. They explode as supernova, and in that final, blinding flash of energy, they fuse the raw ingredients of the universe into heavier elements. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that powers reactors, all were born in such titanic blasts. These newly forged elements were then scattered into space, mixing with the galactic debris. Our own solar system eventually formed from a cloud of gas and dust that had been enriched by these ancient intergalactic fireworks. So every time you feel your pulse, you are feeling the echo of a stellar explosion triggered by a galactic collision that happened billions of years ago, far beyond the Milky Way. This profound connection shows that our planet's material foundation was built by forces operating on a truly cosmic scale. But the influence of these distant galaxies did not stop with our planet's raw materials. The very architecture of our solar system, its position and its structure, was also shaped by powerful external forces. Our serene journey through the galaxy is far from smooth. Every 250 million years or so, as our Sun completes its grand orbit, it carries our entire solar system through the Milky Way's dense spiral arms. Think of these arms not as static structures, but as cosmic traffic jams, regions where stars, gas, and dust are packed together more tightly. This regular passage may have left a hidden signature on our world. Some scientists suggest that when we move through these crowded arms, the increased density of interstellar material presses inward on the heliosphere, the vast protective bubble of particles blown out by the solar wind. A slightly compressed heliosphere could be a slightly weaker shield. This might allow a greater influx of high-energy cosmic rays from deep space to penetrate into our inner solar system and reach Earth's upper atmosphere. Here, a fascinating chain of events could unfold. These cosmic rays are thought to seed the formation of low-level clouds, which reflect more sunlight back into space. More clouds could lead to a cooler planet, potentially triggering or prolonging an ice age. The evidence is etched into our geological record, in the rhythmic advance and retreat of glaciers that seem to pulse in time with our galactic orbit. The very architecture of our home galaxy, therefore, may have been the silent metronome setting the tempo for Earth's climate, determining when vast ice sheets grew and when they retreated to shape the landscapes we know today. This profound link between galactic geography and terrestrial climate reveals a solar system deeply connected to its environment. Yet the stability that allowed life to flourish for billions of years might depend on an even more fundamental and invisible galactic presence. Our perfect location in the Milky Way was not a matter of chance, but a consequence of galactic real estate. Just as a planet needs to orbit within a star's habitable zone for liquid water, a solar system must reside in a galactic habitable zone for complex life to have a chance. This is a narrow, sweet spot within the vast spiral. Venture too close to the galactic center, and you face a constant barrage of lethal radiation from the supermassive black hole and the densely packed stars, an environment that would strip away atmospheres and bombard any emerging life with sterilizing energy. Yet drift too far out into the galactic hinterlands, and you find a cosmic desert, desperately poor in the heavy elements necessary to build rocky planets at all. Our solar system orbits in this privileged suburban ring, a region rich with the metallic ashes of long-dead stars, yet quiet and stable enough for a delicate world to endure. This peaceful neighborhood allowed Earth to form from a dusty disk without constant disruption, to hold onto its water and atmosphere for billions of years, and to slowly cultivate the chemistry of life. The grand architecture of our galaxy itself carved out this safe harbor, setting the stage for everything that followed. But the specific ingredients for life on Earth may have been delivered by messengers from even further away, from stars that lived and died in galaxies beyond our own. This invisible rain from deep space is not just a background hum, it is a potential agent of change. The highest energy cosmic rays are atomic nuclei traveling at nearly the speed of light, propelled across the void by the most violent engines in the cosmos. Their origins are cosmic cataclysms, like the supermassive black holes at the centers of active galaxies, where matter is torn apart and spat across the universe. When one of these rare, hyper-energetic particles slices through our atmosphere and reaches the surface, it can pierce a living cell. Its passage is a microscopic event of immense power, capable of snipping a DNA strand or altering its delicate code. Most of the time, such damage is repaired or leads to nothing. Sometimes it is harmful, but on exceedingly rare and pivotal occasions, that random change written by a particle from a distant quasar might just offer an advantage. It could be a mutation that allows a plant to better conserve water, or an animal to process a new food source. Over millions of years, this cosmic lottery has been running continuously, its outcomes woven into the fabric of life's immense family tree. The very diversity of species that walk, swim, and fly across our planet may owe a subtle debt to these intergalactic messengers. This profound link suggests that the story of life is not confined to Earth's biology, but is also written in the violent heart of distant galaxies. And the cosmic influence on life's story began long before the first cells evolved, with the delivery of its most fundamental building blocks. The very water that defines our blue planet holds a secret older than the sun. We live on a world dominated by oceans, yet the origin of all this water has long puzzled scientists. How did a rocky planet forming in the hot, inner region of a newborn solar system acquire such a vast quantity of the liquid of life? The answer appears to lie far beyond our galaxy's borders. A compelling theory suggests that a significant portion of Earth's water has a truly extragalactic origin. In the frigid, vast darkness between stars, water molecules slowly form on the surfaces of tiny dust grains, building up as layers of ice. When our solar system was just a swirling protoplanetary disk, it is believed that a relentless bombardment of icy comets and asteroids delivered water to the young, molten Earth. But many of these icy messengers were not native to the primordial cloud that birthed our sun. They were cosmic immigrants containing water forged in the molecular clouds of other, smaller satellite galaxies that were gravitationally shredded and absorbed by the Milky Way long ago. Spectroscopic observations confirm that water is a common, widespread molecule even in distant galaxies. Therefore, every raindrop that falls, every wave that crashes on a shore, and every glass of water you drink may contain molecules that have traveled across the immense void of intergalactic space. Our oceans are a cosmic cocktail, a mixture of ingredients sourced from multiple galaxies, blended together in the crucible of our solar system. This celestial delivery service did not stop with water. The same violent stellar deaths that enriched our galactic neighborhood with heavy elements also provided the specific ingredients for life itself. Floating beside the Milky Way, the Magellanic clouds appear as ethereal wisps of cosmic light. These are not mere clouds, but entire dwarf galaxies, each a bustling realm of stellar birth and death. Within their boundaries, massive stars live fast and die young, culminating in supernova explosions of staggering power. These blasts are so violent they can hurl newly forged elements directly into the emptiness between galaxies. Sophisticated computer models reveal a startling journey for this material. Clouds of gas enriched with carbon, the fundamental element of life structures, oxygen for the air we breathe, and nitrogen for our very DNA, are ejected at such incredible speeds they break free from their home galaxy's grasp. This elemental shrapnel then voyages across the dark intergalactic sea, a journey that can last for millions of years. Eventually, the immense gravity of our Milky Way captures these wandering clouds, pulling them into the galactic mix from which new stars and planets will form. This means the very chemistry of life on Earth is not solely a local product. The carbon in your body, the oxygen filling your lungs, was partially forged in stars that lived and died in these small companion galaxies. Our biosphere was fertilized by a form of intergalactic pollution, a gift of stardust from celestial neighbors, and this cosmic recycling process applies not just to the elements of life, but to the very ground beneath our feet, the dust from which our world was sculpted. The ground beneath your feet holds a secret more ancient than our planet. Drifting in the profound emptiness between galaxies are microscopic grains of dust, a fine cosmic powder forged in the winds and final explosions of stars from countless different galaxies. This is not ordinary dust. It is a mixture of silicates, carbon, and other compounds, a pristine archive of elemental history. As the Milky Way voyages through space, it acts like a giant net, sweeping up this primordial material from the intergalactic medium. When our own solar system began to coalesce from a collapsing cloud of gas and dust, it was not just local material that swirled into the mix. These ancient intergalactic grains, some older than the Milky Way itself, became fundamental ingredients in the protoplanetary disk. They served as the first solid seeds, the nucleation points around which the first crystals and mineral fragments could form. This process directly influenced the chemical variety of the asteroids and planetesimals that later collided and merged to build our world. The staggering diversity of minerals we find on Earth, from common quartz to rare gemstones, owes a profound debt to this cosmic inheritance. Our planet's geological richness was seeded by dust from galaxies that no longer exist, a legacy written in stone. Yet this invisible dust is not the only ghostly substance shaping our world from the shadows. Deep beneath the crust, the immense heat of Earth's core churns molten iron, powering the magnetic field and driving the slow drift of continents. This geological engine has run for billions of years, and its primary fuel has always been attributed to the radioactive decay of elements like uranium and thorium deep within the planet. But there might be another, more exotic source of heat contributing to this vital process. Every galaxy, including our own, is embedded within a vast, invisible halo of dark matter. This mysterious substance, which makes up most of the universe's mass, does not emit or absorb light, but its gravitational pull is undeniable, sculpting the cosmos on the grandest scales. While dark matter mostly passes through ordinary matter like a ghost, some theoretical models propose that a tiny fraction of these particles can be captured by the immense gravity of a planet like Earth. Over eons, they could accumulate in the planet's dense core, and here is where the theory becomes truly fascinating. Certain types of dark matter particles are thought to be their own antimatter counterparts. When two such particles meet, they would annihilate each other in a flash of pure energy. This continuous, slow-burning process of annihilation deep within our planet could be releasing a steady trickle of heat, supplementing the warmth from radioactive decay. This external heat source, drawn directly from our galaxy's invisible halo, might be helping to keep Earth's core molten and dynamic. Without it, the geodynamo that generates our protective magnetic field could have weakened long ago, and the vital engine of plate tectonics, which recycles carbon and regulates our climate, might have ground to a halt. The very ground we stand on, it seems, is warmed not only by the heart of our own world, but by the ghostly presence of the entire galaxy. And this cosmic connection extends far beyond our planet's internal furnace, influencing the grand structure of our entire solar system. The universe is structured like a colossal spiderweb, with galaxies strung along vast filaments of dark matter, separated by immense, empty voids. This cosmic web is not a static sculpture. Its gravitational field is a dynamic force that tugs on everything within it, including our own galactic neighborhood. The collective gravity of these immense filaments and dense nodes pulls our entire local group of galaxies on a specific trajectory through space. This grand river of motion, flowing for billions of years, creates a subtle but persistent background tug on the Milky Way itself. That distant pull, originating from the largest structures in existence, can ripple all the way down to our solar system's outer frontier. It gently perturbs the Oort cloud, that distant, icy shell of comets far beyond Pluto. These perturbations can act like a gravitational hand, shaking loose a shower of icy bodies from their stable orbits and sending them on a long fall toward the inner solar system. Some of these comets might swing harmlessly by the Sun, while others could be set on a collision course with Earth. The geological record holds evidence of periodic mass extinctions, events that cleared the stage for new forms of life to emerge. It is a profound thought that the demise of the dinosaurs, an event that ultimately made room for mammals to rise, might have been set in motion by the gravitational influence of the cosmic web. The largest architecture in the universe may have directly influenced the course of life's evolution on our small planet, and the forces that shape this web can also generate explosions so powerful they can be seen from the farthest reaches of space. A flash of light from a galaxy halfway across the universe could rewrite the story of life on Earth in a matter of seconds. We have witnessed the birth of gamma-ray bursts, the single most luminous explosions since the universe began. They are the death cries of the most massive stars, collapsing into black holes and firing off twin jets of concentrated energy at nearly the speed of light. If such a cataclysm were to occur within a few thousand light-years of Earth, and if one of those narrow, furious beams were pointed directly at us, our planet would be bathed in an intense flood of gamma radiation. This invisible light would not gently warm the surface, it would violently tear apart the very fabric of our atmosphere. The high-energy photons would smash into molecules of nitrogen and oxygen, breaking their atomic bonds and forcing them to recombine into new destructive compounds. The sky would fill with nitrogen oxides, chemicals that act like a corrosive acid for the ozone layer. Our protective shield against the sun's most harmful ultraviolet rays would be systematically and catalytically dismantled, molecule by molecule. Without this layer, the planet's surface would be exposed to a sterilizing glare. Land plants would wither, the base of the ocean's food web would collapse, and any animal life caught in the open would suffer devastating genetic damage and cancers. The geological record holds evidence of several mass extinctions whose precise cause remains a mystery. One of these ancient die-offs, a moment when life was nearly erased, could have been triggered by a stellar collapse in a faraway galaxy, its lethal breath taking millions of years to cross the void and find us. This threat is a humbling reminder that our planet's delicate habitability exists at the mercy of stellar drama unfolding millions of light years away. Yet the very possibility of such a cataclysm, and indeed the existence of any life at all, hinges on a set of rules so precise they feel like a cosmic conspiracy. The fundamental rules of reality appear to be a perfect recipe for our existence. The strength of gravity, the power that holds galaxies together, is precisely what it needs to be. If it were even a tiny fraction stronger, the universe would have collapsed back on itself in a fiery crunch moments after it began. If it were slightly weaker, matter would have flown apart so rapidly that not a single star could ever ignite. This perfect balance is not limited to gravity. The nuclear forces that operate inside every atom are also exquisitely tuned. They govern how protons and neutrons stick together to form the nuclei of elements. For life, one element stands above all others: carbon. The journey to create carbon inside stars is a cosmic tightrope walk. When three helium nuclei collide to form a single carbon nucleus, the reaction relies on a precise energy resonance. It is as if the star's core and the emerging carbon are singing exactly the same note, allowing them to fuse together efficiently. Without this specific, finely tuned resonance, the reaction would fail. Stars would produce only a trickle of carbon or none at all. The universe would be a barren place, devoid of the chemistry that life requires. This perfect alignment of physical constants was locked into place during the universe's first fleeting instance, a foundational settings menu for all of creation. The same laws that govern the spin of a distant galaxy cluster also dictated the successful forging of the very atoms in your body. This cosmic fine-tuning connects our most intimate existence to the primordial epoch of everything. And this invisible architecture extends to another pervasive force, one that guides the birth of stars across the cosmos and may have even shaped our own solar system. We cannot see them with our eyes, but our galaxy is threaded with invisible lines of magnetic force. These vast, ghostly fields stretch between the stars, acting as cosmic highways for high-energy particles and invisible scaffolds for the clouds of gas that will one day collapse into new suns. The origin of these galaxy-spanning magnetic fields is one of astronomy's great puzzles. How did such an organized force come to permeate our entire Milky Way? The answer may lie in the universe's first moments. One compelling idea suggests that these fields were born from the violent turmoil of the cosmos' infancy, seeded by primordial processes like the shifting of fundamental forces in the instant after the Big Bang. Alternatively, the first stars and galaxies might have generated the initial, weak magnetic fields through their powerful winds and explosive deaths. These fledgling fields, weak as they were then captured and woven into the fabric of the galaxy as it assembled itself over billions of years. Spun and amplified by the slow, churning motion of galactic gas, they grew into the immense magnetic structures we detect today. This magnetic environment was not a passive bystander in the story of our Sun. When a cloud of gas begins to collapse under its own gravity to form a star, it must shed its rotational energy. Magnetic fields provide a crucial braking mechanism, helping to slow the cloud's spin and channel material inward. Without this magnetic assistance, the process of star formation would be far less efficient, and many potential stars, including stars like our own Sun, might never have ignited at all. The very existence of our solar system, therefore, may hinge on magnetic seeds planted in the cosmic dawn. This galactic inheritance did not arrive in a steady stream, but was dramatically reshaped by violent encounters from our galaxy's past. Our galaxy's serene spiral shape hides a violent history of collisions. Around 10 billion years ago, a massive dwarf galaxy, now known to astronomers as Gaia Sausage-Enceladus, plunged directly into the young Milky Way. This was not a gentle merger but a catastrophic impact that fundamentally reshaped our galactic home. The intruder galaxy was utterly shredded by gravitational forces, its stars scattered into a chaotic, spherical halo that still surrounds the Milky Way's disk today. This ancient cataclysm did more than just add stars. It sent powerful gravitational shockwaves rippling through the entire galaxy. These waves would have compressed vast clouds of primordial gas, likely triggering a firestorm of new star formation. One particular cloud, rich with the elemental ashes of earlier stellar generations, was caught in this cosmic turbulence. As it collapsed under its own gravity to form our Sun and its planetary disk, the specific trajectory and spin of that cloud were likely imprinted by the Gaia Sausage-Enceladus merger. The angular momentum that dictated the flat plane of the protoplanetary disk and the stable, nearly circular orbit that Earth now enjoys around the Sun might have been set in motion by that long-ago collision. Without this galactic encounter billions of years before the Sun even ignited, our solar system might have formed on a wildly different, unstable path, a place where a life-bearing planet like Earth could never have survived. The very regularity of our seasons and the stability of our climate are a quiet legacy of this primordial violence. This deep historical context, written in the motions of stars, sets the stage for understanding the different stellar populations that surround us. Our Sun is not a solitary pioneer but a descendant of ancient stellar dynasties. Across the Milky Way, stars are sorted into distinct populations, a classification based on their metallicity, which is simply the amount of elements heavier than helium they contain. You can think of it as a cosmic family tree written in starlight. Population 2 stars are the ancient, metal-poor grandparents of the galaxy, formed from the pristine hydrogen and helium of the early universe. Our Sun, by contrast, belongs to the younger population 1 group, stars rich in metals that orbit within the galactic disk. This distinction is not merely academic, it is the single most important reason our world exists at all. The Sun is a third-generation star, meaning its raw material was enriched by the life and death of 2 previous generations of stars. Those prior stellar generations seeded the interstellar cloud with the specific heavy elements necessary to form rocky planets. Without this prior enrichment, the protoplanetary disk around our newborn Sun would have been a sparse and simple place. The crucial metals, elements like iron, silicon, and magnesium, condensed into microscopic dust grains as the disk cooled. These solid particles were the essential seeds, the first pieces of grit around which the first planetesimals could clump and grow through countless collisions. The specific chemical signature of that long-vanished cloud, a cocktail of elements forged in supernova across the galaxy, was stamped directly onto the forming Earth. A star born with a different metallicity, either too poor or too rich in these heavy elements, would have constructed a completely different planetary system, one almost certainly devoid of a stable, rocky world with a metallic core and a solid mantle. The very ground we stand on is a direct inheritance from the Sun's specific stellar ancestry, a lineage written into the galaxy's gradual chemical evolution. This intricate chain of cosmic inheritance, however, reaches down to a scale far smaller than atoms, to the ghostly particles that barely interact with our world at all. Every second, trillions of ghostly particles from distant galaxies are passing directly through your body without a trace. These are neutrinos, and while most come from our own sun, a faint but constant drizzle originates from far more spectacular sources across the universe. This cosmic neutrino background carries the faint whispers of supernova that exploded in other galaxies billions of years ago, the violent mergers of neutron stars, and the furious jets erupting from active galactic nuclei. Each of these nearly massless particles is a tiny messenger, traveling for eons across the vast emptiness of intergalactic space, barely interacting with anything along the way. Their collective presence forms a living fossil record, a low-energy hum that permeates all of space, including the room you are in right now. This relic background is a direct imprint of stellar and galactic activity throughout cosmic time, a testament to the fact that no event in the cosmos is truly isolated. The nuclear furnaces of galaxies far beyond our own have left a permanent, if subtle, signature that perpetually washes over our world, linking every one of us to the most energetic and distant phenomena in the universe. This invisible connection demonstrates that our cosmic environment is not defined by empty space, but by the history of its most violent events. That very history is also encoded in the fundamental geometry of the universe, a geometry whose expansion has been directly imprinted upon our planet. The lithium in your phone battery is a messenger from the universe's first few minutes. Along with hydrogen and helium, it was forged in the primordial nuclear furnace of the Big Bang, a brief, searing epoch when the entire cosmos was a raging inferno of fundamental particles. Yet this ancient element presents a profound mystery. When astronomers measure the lithium content in the oldest stars in our galaxy, the numbers do not add up. These ancient suns, which formed from the pristine gas of the early universe, contain only about 1/3 of the lithium that our best models of the Big Bang predict they should. This is the cosmological lithium problem, a glaring gap in our understanding of the universe's first nuclear reactions. It means that our foundational story of how the lightest elements were created is somehow incomplete or incorrect. The implications reach all the way to our world because that same primordial lithium, whatever its true amount, was baked into the cloud that birthed our solar system. The trace amounts of lithium found in Earth's crust and in the technology we use every day are direct descendants of that flawed initial endowment. This means the very ground beneath us holds a tangible clue to a fundamental error in our cosmic origin story. So what happened to the missing lithium? The answer may lie not in the beginning, but in the lives and deaths of the very first stars that illuminated the galactic darkness. Their violent ends may have provided a mechanism to destroy that primordial lithium, sculpting the specific chemical landscape from which our planet would eventually form. The gold in a ring or necklace was born in a cataclysm of unimaginable violence, the collision of two dead stars. These are neutron stars, the ultra-dense cores left behind after supernova explosions, each one so compressed that a single teaspoon of its material would weigh billions of tons. When two of these cosmic ghosts spiral into each other, they do not meet quietly. Their merger, known as a kilonova, unleashes a fireball of energy and ripples the very fabric of spacetime with gravitational waves. For a few dazzling seconds, this event outshines entire galaxies, but its true legacy is forged in the aftermath. The immense forces at play tear material from the neutron stars, creating a swirling, superheated cloud incredibly rich in neutrons. Within this neutron-rich environment, atomic nuclei are bombarded, capturing neutrons at a staggering rate in a process called the rapid neutron capture process. This is the universe's primary factory for the heaviest elements, the place where atoms of gold, platinum, and even uranium are assembled from the debris of stellar corpses. These newly minted elements are then blasted outward at incredible speeds, a glittering, radioactive shrapnel cloud expanding into the galactic void. Our own solar system's birth cloud appears to have been seeded by such an event. Scientific models indicate that a single, nearby kilonova occurring within 100 light-years of our pre-solar nebula, and in the relatively recent cosmic past before the Sun formed, could account for the entire abundance of these precious heavy elements found on Earth today. This means the uranium that fuels power plants and the platinum in catalytic converters are not just extraterrestrial, they are intergalactic travelers. Their atoms were forged in a titanic merger that may have occurred in a small, satellite galaxy since consumed by the Milky Way. Every piece of gold is a solidified piece of a cosmic catastrophe, a direct physical link to one of the most energetic events since the Big Bang. This narrative of enrichment, of our planet being seeded from afar, extends beyond these rare metals to the most fundamental element of life itself. The carbon that forms the ink in this sentence was once buried deep inside a dying star. Far from the bustling spiral arms of the Milky Way, in the sparse galactic halo, aging suns enter their final, dramatic phase of life. These are asymptotic giant branch stars, swollen to colossal sizes, their internal furnaces churning violently. Deep within their cores, a process called dredge-up occurs, where newly forged carbon is hauled up to the surface by powerful convection currents and ejected into space on stellar winds. The star essentially coughs its own atomic innards out into the void, surrounding itself with a beautiful, glowing shroud we call a planetary nebula. This cosmic soot, rich in carbon and other elements, drifts for eons. When the cloud that gave birth to our solar system coalesced, it was already seeded with this gift from countless, long-vanished halo stars. The specific abundance of carbon on our planet, the very element that defines organic chemistry, was set by this large-scale galactic recycling program. Every living thing on Earth is part of a grand carbon cycle, moving atoms from the air to plants to animals and back again. But the energy that drives this entire biological loop was originally locked into those carbon atoms by nuclear fusion in distant, dying suns. The breath you just took contains carbon atoms that were forged in the heart of an HB star that shone billions of years ago, in a region of the galaxy far from our own. This steady rain of stardust from the halo ensured our world would be a carbon-rich planet, a world capable of building the complex molecules of life. Yet the distribution of these vital elements was not uniform, and our planet's journey through the galaxy may have taken it through regions of profound emptiness that shaped its destiny in a completely different way. Just beyond our galactic neighborhood lies an immense and startling emptiness. This is the local void, a region of space spanning hundreds of millions of light-years where galaxies are almost entirely absent. Emptiness in the cosmos is not passive. It exerts a kind of negative gravitational pressure, a gentle but persistent push. Galaxies naturally flow away from these under dense voids and toward the most crowded regions, like water draining from a hill into a valley. Our entire local group, including the Milky Way, is being subtly repelled by this void, nudged on our course through the intergalactic medium. This grand, slow-motion drift directly shapes the local environment of our solar system. As we voyage, we move through pockets of interstellar gas with varying density and pressure. Think of it as a ship sailing through waters that are sometimes calm and sometimes choppy. When the external pressure from this gas increases, it can compress the heliosphere, the vast protective bubble of charged particles blown out by the solar wind. A slightly squeezed heliosphere is a slightly weaker shield. This can allow a greater number of high-energy galactic cosmic rays to leak through into our inner solar system. These cosmic rays are atomic nuclei accelerated to nearly the speed of light by distant supernova and black holes. When they reach Earth, they can influence cloud formation in the upper atmosphere, potentially altering global climate patterns over long timescales. So the great cosmic nothingness of the local void, by influencing our galaxy's motion, indirectly tweaks the invisible forces that shape our planet's environment. This profound link between a nearby emptiness and our terrestrial climate reveals a universe where even nothing is something, and this grand motion through the cosmos is ultimately guided by the first and most ancient light of all. For hundreds of millions of years after the Big Bang, the cosmos was a featureless, opaque sea of hydrogen gas. This primordial fog was so thick that light could not travel freely, trapping the universe in a perpetual, formless twilight. Then the first stars and galaxies ignited, pouring torrents of ultraviolet radiation into the void. This marked the beginning of a titanic transformation known as reionization, a process where that intense starlight systematically stripped electrons from the neutral hydrogen atoms, burning away the cosmic fog and clearing a path for light to travel across the universe. The pace of this great clearing was everything. Had it unfolded too slowly, the lingering hydrogen fog would have stifled the growth of later galaxies, starving them of the light needed to regulate their formation. But if it had progressed too rapidly, the intense radiation might have shredded the fragile gas clouds in small, budding galaxies, preventing them from ever coalescing into stable structures like our Milky Way. The fact that reionization concluded at just the right moment, sculpted by the collective output of countless early galaxies, was a prerequisite for the eventual emergence of a calm, structured spiral galaxy. Our ability today to peer billions of light-years into space with telescopes to see galaxies in their infancy is a direct gift from that ancient epoch of light. This clear view of the cosmos was hard-won, and the galactic environment it helped create was further shaped by a retinue of smaller celestial companions. That vast, ethereal ribbon of gas arcing across the southern sky is more than a celestial curiosity. The Magellanic Stream is a river of creation in motion, a direct and visible testament to our galaxy's ongoing appetite. Stretching for hundreds of thousands of light-years, this colossal filament of hydrogen was torn by gravitational tides from the Magellanic Clouds, those two small companion galaxies orbiting our own. It is a river of pristine fuel, gas that has been relatively untouched by the polluting cycles of stellar death and rebirth. Over the coming hundreds of millions of years, this stream will slowly rain down upon the Milky Way's disk, falling into the galactic reservoir. There it will mix with denser clouds, eventually collapsing under its own gravity to ignite a new generation of stars. Our own sun may be middle-aged and the Earth long-formed, but this process demonstrates that the galaxy itself is still under construction. It is a living, breathing entity, actively gathering the raw materials for its future from its celestial neighbors. This constant, gentle rain of intergalactic gas reveals that the story of cosmic inheritance is not confined to the ancient past. It is a continuous cycle of growth and renewal, a dynamic relationship that connects every galaxy to its satellites in an unbroken flow of matter. This grand, ongoing accretion forces us to confront a deeper question about the destiny of all we see. The very fabric of empty space seems to be pushing the cosmos apart. This is dark energy, a mysterious repulsive force woven into the vacuum itself, driving the universe into an ever faster expansion. For now, its effects are felt only on the largest scales, a gentle but relentless pressure acting between galaxies. But this acceleration has a profound and ultimate consequence for the future of cosmic evolution. As the expansion quickens, the great rivers of intergalactic gas that currently flow into galaxies will be stretched thin, and the gravitational pull between neighboring galaxy clusters will weaken. The growth of new cosmic structures will effectively cease. The universe is destined to become a much lonelier and darker place, a vast expanse where island galaxies drift endlessly apart, their stellar furnaces slowly cooling and dying out. The fact that we exist now in an epoch where galaxies are still close enough to collide, to gravitationally stir the pot and trigger the birth of new stars, is not a mere accident of timing. This current stellar era, a finite window in cosmic history, was the only possible time for a planet like Earth to form. It required the prior generations of stars to have lived and died, seeding the galaxy with heavy elements, and it required the ongoing galactic interactions to compress gas clouds and spark the formation of our own sun. The specific strength of dark energy, a seemingly arbitrary number, has set the duration of this fertile period. Had this vacuum energy been slightly stronger, the universe would have accelerated apart before any galaxies could properly form. Had it been weaker, the cosmos might have collapsed back on itself long ago. Our existence is therefore pinned to this narrow sliver of cosmic time, a direct result of the vacuum's hidden properties. This cosmic stage, set by a force that operates across billions of light years, finds a strange and parallel echo in the chaotic, probabilistic world of the very small. The largest structures in the cosmos were born from the smallest possible vibrations. In the first fleeting sliver of a second after the Big Bang, the universe underwent a period of hyper-fast expansion known as inflation. During this unimaginably brief epoch, the empty vacuum of spacetime itself was not perfectly smooth. It was a seething, foaming sea of quantum uncertainty, where pairs of virtual particles flickered in and out of existence. These are quantum fluctuations, temporary bubbles of something and nothing that appear and vanish constantly. The rapid stretching of inflation did something incredible to these tiny ripples. It grabbed them and stretched them from a subatomic scale to a cosmic one, freezing them into permanent, microscopic variations in the density of the newborn universe. These frozen wrinkles became the gravitational seeds for all future structure. Imagine a perfectly smooth sheet of rubber suddenly covered in a fine, random pattern of bumps. Over billions of years, gravity would act like a magnet, pulling matter toward those tiny bumps. The slightly denser regions would attract more and more gas, eventually collapsing under their own weight to form the first stars, the first galaxies, and the great filaments of the cosmic web we see today. The specific pattern of those initial quantum ripples determined everything that followed. It decided where galaxy clusters would form and where vast, empty voids would remain. This means the very reason our Milky Way galaxy exists in its specific location, with its specific mass and structure, can be traced back to a random quantum jitter that occurred in the first trillionth of a second of time. The gravitational environment that pulled our solar system together, that provided the stable galactic suburb we call home, began as a subatomic tremor. This ultimate connection between the quantum and the cosmic forces us to confront the final, and perhaps most personal, link in our chain of origins. Time flows in one direction only, from a past of intricate order towards a future of inevitable disorder. This one-way street, the arrow of time, is not just a feature of our daily lives but a fundamental property of the cosmos, rooted in its very first moment. The universe began in a state of incredibly low entropy, a condition of exquisite and improbable order, like a perfectly stacked deck of cards. From that singular point, everything has been unfolding, spreading out, and becoming more randomized. This relentless climb towards higher entropy is not mere chaos. It is the engine that drives cosmic evolution. It powers the gravitational collapse that ignites stars, the violent mergers that build galaxies, and the internal differentiation that gives planets like Earth a molten core and a solid crust. The entire geological and biological history of our world is a direct expression of this cosmic imperative. Earth's story, from its fiery accretion to the slow march of life, is a local eddy of incredible complexity swirling within the great river of increasing disorder. This beautiful, temporary rise in complexity on our planet was only possible because of that specific, finely tuned initial state of the universe. Our history is a single, eloquent chapter in the grand narrative of cosmic evolution, a narrative written by the relentless pull of time itself. Having traced these 24 profound connections, from the iron in our blood to the arrow of time guiding our history, a single, unifying truth emerges. We are not merely living in the universe, we are a living, breathing expression of its deepest history and most fundamental laws. These threads of cosmic history are not separate strands, but a single, woven tapestry. Every discovery we have made, from the galactic collisions that forged our star's cradle to the quantum ripples that seeded our galaxy's location, points to an undeniable truth. Earth is not a solitary world that simply appeared. It is a cosmic concentrate, a distillation of events from across the universe and across time. The iron that carries oxygen through your veins was forged in a star born from galactic cannibalism. The water that fills our oceans fell as ice from intergalactic space. The gold in a ring is the glittering debris from a neutron star collision that may have occurred in a galaxy long since consumed by our own. Even the fundamental rules of reality, the precise strength of gravity and nuclear forces, were set in the first moments of creation to allow for carbon-based life to one day arise. This intricate chain of causality means the Milky Way's violent mergers, the gentle reign of dark matter, and the repulsive force of dark energy are not just distant curiosities. They are active participants in our story, the essential conditions that conspired over billions of years to create a stable, watery world in a quiet galactic neighborhood. To see our planet in this light is to undergo a profound shift in perspective. Home is no longer just this blue marble, but the entire cosmos that labored for eons to bring it into being. We are not just living in the universe is living within us, its history written into our very atoms. This realization brings us to a final, deeply personal reflection on our place within this grand narrative. This grand tapestry of connections reveals a cosmos that is both deeply interconnected and intimately personal. We are far more than inhabitants of a planet. We are the universe itself, having slowly awakened to contemplate its own spectacular origins. Every piece of this story, from the iron in our blood to the lithium in our batteries, is a souvenir collected across an epic journey through space and time. The carbon in our cells, the ground beneath our feet, and the air we breathe are not merely resources, they are relics. They are the tangible evidence of galactic collisions, stellar explosions, and quantum tremors from the dawn of everything. As the astronomer Carl Sagan so beautifully observed, the cosmos is within us. We are a way for the universe to know itself. Let this profound truth ignite two powerful feelings within you. The first is a boundless sense of wonder, a sheer awe for the intricate, improbable chain of events that conspired over billions of years to allow you to be here, conscious and able to understand it. The second is a deep sense of responsibility. This Earth is not just a rock, it is a cosmic oasis, a rare and precious concentration of the universe's entire history. Protecting this fragile world means honoring that epic journey. If this exploration has shifted how you see your place in the cosmos, we would love to hear your reflections. Share your thoughts in the comments and subscribe to join us as we continue unraveling the profound mysteries of the universe.